Hey class, I told you that I would follow up with you whenever I got the arguments on Fermat's last theorem correct. I've finished the work on it, but the video is entirely optional, and we've already spent enough class time on it that I only wanted to include this as a one-off. So let's run through it, and you can be done with it for as long as you want to be done with it. Okay. Okay, so we kind of restate the spirit of what we had initially tried to prove, and then we're going to run through it again, but handling some of the squirrely cases. Okay, so essentially anything of this form, we state it has to obey the triangle inequality, and then if it does obey the triangle inequality, then we can represent it as a point on the unit circle, dividing both sides, and then equating this to cosine squared theta and this to sine squared theta. And with that equation, we have it in this form, and then we want to show that n is equal to 2 because cosine of theta and sine of theta are both rational, and because they're rational in a way that you can't promote some exponent from that rational representation. As you'll see, we can construct it so that we can get a promotion from one but not from both. And because n is dependent on, like, n is constant between the two equations, since you can't get both, then there is no counterexample to Fermat. Okay. And so this essentially restates it. So this is rational, so n must be 2. All right. Okay, so running through what we've already covered, if you have something of this form, then it has to obey the triangle inequality, and it has to be either a right or an acute triangle. This states that if c is already greater than a plus b, then in exponential form you see that e to the n to the times natural log of c is going to outrun the sum of these other two. If a plus b is exactly equal to c, so that these are segments of c, then c squared is equal to a plus b all squared, and so this will leave an additional 2ab plus a squared plus b squared, so you see that it's greater. If c is an obtuse angle, then cosine of c is less than 0, and in particular negative 2ab cosine of c is greater than 0, right? Negative of the negative is positive. And so the law of cosines tells us that c squared is greater than a squared plus b squared in such a case. So it has to be a triangle, and it has to be either right or acute. So solutions of this form can be represented as a point on the circle, so we clean. So from the above, we see that it has to obey the triangle inequality. We also have discussed how it's a family of triangles, and so from ABC, the triple ABC, up to any choice k less than n, at which point we have equality and the triangle inequality goes away. Right? So if we choose k between 1 and n, then we have this triple, which represents a triangle, and then we see from this form that it, in fact, because the Pythagorean identity holds, the Pythagorean theorem holds, we have that it is a right triangle. Right? So this is the triple we're going to analyze. So we don't know whether or not any of these numbers are natural numbers. We only claim that they represent a right triangle. And because of that, we can treat a to the k and b to the k as coordinates on the complex plane. So z is equal to x plus iy, and the modulus of z, the absolute value of it, is equal to c to the k, which makes sense because the modulus of z is the hypotenuse of that right triangle. So in polar form, we have z equals rho ei theta. We've already established that rho, the modulus, is equal to c to the k. E to the I theta is cosine theta plus I sine theta. Expanding and distributing, we get this form, and then we get, as expected, and we already knew that this was equal to x plus iy. But now we can say that x, which is equal to a to the k, is also equal to c to the k cosine theta. Y, which is equal to b to the k, is also equal to c to the k sine of theta. And then just moving everything to the right, we have cosine of theta is a to the k over c to the k, or alternatively a over c all to the n over 2. Likewise for sine, b to the k over c to the k, and that's equal to b over c n over 2. Okay, so we have points on the circle. The first thing we want to discuss is the rational points on the circle. So we know that b over c and a over c are both rational, and we know that we're dealing with an n at the end. So it makes sense to consider first the rational points on the circle. And so we say that these points, when cosine of theta and sine of theta are equal to 0, have no extricable exponents. So we can't have it be a rational point and then extract some exponent from it and still have it be a rational point. And in particular, we emphasize that that's for both. So as you'll see, we can construct points which do offer up an exponent for one of the terms, but never both. You can never have both at the same time be reducible by some exponential power. Okay, so to get the rational points on the circle, we rely on the parametrization formula, which should already look a lot like Euclid's formula for generating Pythagorean triples. But the parametrization we'll use to get both the algebraic points, which are interesting to us, and right now the rational points. So rational input gives you rational output, and we get that by substituting t equals p over q, where p and q are both natural numbers. So then we make that substitution, and we see that the real component x ends up with this formulation, and the imaginary component y ends up with this formulation. Okay, so then if we consider just the unscaled real valued ratio, so we had a to the n to begin with, we see that we have to obtain it from q squared minus p squared. So let's say that we are able to find something that has some extricable exponent. So the way we would do that, remember that we observed that there was this progression, q squared minus p squared, q squared, and then q squared plus p squared. So we should expect something in that range. We should expect to be able to find some midpoint between two perfect powers. So let's solve for it explicitly, but let's solve for it just for the unscaled term right now. So then if we set q to be such a midpoint, so pick some arbitrary integer x2, which is larger than x1, and then exponentiate both terms. And if you take their average and we assign that to be q, and then you take p to be the difference, the half of the difference between them, so that q minus p gets you a perfect power, and so that q plus p gets you a perfect power. Then when we expand this into q minus p times q plus p, then we end up with making our substitution. So q is exactly equal to this, p is exactly equal to this, and we're just substituting algebraically right now. Then we see that this minus this, the x terms cancel out, the negative cancels out here, and so we get 2x1 to the n over 2, and that reduces to x1 to the n. And over here we get the opposite, where we get x2, sorry, the x1's x1 minus x1 cancels out, and we get 2x2 to the n over 2, which becomes x2 to the n. And so we are able to just construct a point which is a perfect power in this form. So we can construct as many of these points as we want. It's not difficult. Okay, so, and because we made no restriction on it, all we required is that x1 and x2 be natural numbers, and that x1 be less than x2, then we can construct all of the perfect powers in this form, right? Okay, so then in doing so, we can now substitute in for the other formulation. Okay, and so we have that. Sorry, we have our algebraic substitution. So starting with 2qp, right? So the unscaled imaginary component. So this is q, this is p. We multiply them together. This becomes x. So this 2 cancels out this 2. There's a half left over, and then these merge together to become x2 to the 2n minus x2, or x1 to the 2n. And then our denominator, again, just straight substitution, multiply it out, add them together, this cancels, and we end up with something of this form. So now we piece together our ratios to see whether or not we can extract an exponent. There is an exponent to be had right here, but whenever we divide it by q squared plus p squared, this 2 comes out in the numerator, this factor of 2, which is a little bit troublesome. But then we have that this is an integer. And then if we do the imaginary component, we make our substitutions, then we end up with this ratio. Then this 2 cancels this 2. This 2 moves to the numerator to cancel this 2. And we end up with this form. And so it looks like the forms just kind of flop back and forth. So we're always in something like this. But if we perform this exercise one more time, and it's dubious whether or not we could find such x1 and x2, but hey, if there are solutions to Fermat, then we should be able to find such points. Right? So now we choose x2 to the n and x1 to the n, which are midpoints to this sum and midpoint to the difference. So now, following the same exercise as before, we make our substitutions in for the previous form. Right? And now we get x3 and 4 to the 2n, and then when we substitute what was once our almost perfect power, then we end up with this, and so now we have again a difference of now something that's to a fourth power over 2, and then the denominator ends up in this form, so that's going to end up putting a 2 in the numerator again. However, now that we've applied this twice, we have this form and we have this form. And so we can see that somewhere along the line, like regardless of how many exponents you're able to pull out of here, you're going to end up with a 2 in the numerator. So that if you try and extract if you try and pull out this exponent in and promote it, you're going to end up with a radical rather than a rational value. And we know that this will not cancel it out, because this was defined as twice the value of this, so that either the n root of this is going to be not in n, or the n root of this, and that's because this 2 right here, right? So one of these had to be irrational, so that you can't pull it out, you can't get away from it. Okay. So now we take a look at the algebraic points on the unit circle. So again, this time instead of cosine of theta and sine of theta not equal to 0, we have cosine squared and sine squared. And we want to know if something like square root of 3 over 2, if it's possible where you square it, you end up with the rational value, and if once squared, there's some hidden exponent that you can maybe pull out. And so, something like x to the 5, the square root of x to the 5th, well, if you could square it, then you could promote that fifth, and x would presumably be some integer value. So is it possible to construct such a thing? Okay, so again, we use the parametrization formula. So rational inputs give you rational outputs, and radical inputs will initially give you radical outputs, but we're looking at squaring these terms. Okay, so now we can't use p squared anymore, because once we've made our substitution, we have this. And so as a result, rather than using q as our midpoint, we're forced to use q squared as our midpoint. And initially that's really promising, because now we get two perfect powers right out of the gate. We get x1 to the n over x2 to the n. And so now we have to, and so we can solve for q, or we can solve for q squared. We can see what that is, and we know that q is going to be the square root of this. And p is going to be that difference of perfect powers divided by 2. And so we can go into our imaginary component and make our substitutions. Right? So q was the square root of this thing. P was already under the square root. And so square root of 1/2 times square root of 1/2 is 1/2. And so the 2 cancels out here. In the denominator, we have a perfect power. And then under the radical, we have a difference of perfect powers. Okay, so then squaring the ratio overall, we get rid of the radical. There's something in the denominator that looks like it might allow us to promote some exponent in. So this looks familiar. It looks like a geometric series. And so we can construct it as such by defining this to be our ratio. And from that, it really looks like we're not going to be able to extract that nth power. We just have this this power series instead times some fractional value. But if we and so this becomes our b b over c squared term, right? But we can try to find some solution to this, so it doesn't appear as though we're going to be able to get it in this direction. But if we go back to the initial formulation, so a to the n plus b to the n equals c to the n, right? In this case, we use these a squared to the 2n, b to the 2n, and c squared to the 2n, so that we have an integer to a common exponent, right, all across the line. Then we carry through, we follow through with most of it. Then we see that b to the 2n over c to the 4n is equal to 1 minus a to the 4n over c to the 4n. Right? And so now, since this was b to the n over c squared, or c to the 2n, we have something that we can relate it to, and it's going to be solutions from this form. Right? But solutions of this form, we had constructed it so that our points would have radicals, so we've already gotten rid of it. And on top of that, or as a result of that, we ended up with looking for solutions with rational points on the circle, or where we can extract some exponent n from a rational point on the circle. And we've already shown that we can't do that. Right? But if we follow through and we make our equivalence, then on the one hand, we have b to the n over c to the 2n is equal to 1 minus a to the 2n over c to the 2n. Right? And that really follows over here. Right? And so if we square that, then we end up with this additional term. Okay, and then whenever we attempted to extract solutions for that form from this this equation, using rational points, we had this. So we set the two sides equal, the ones cancel out, this moves to the left, this moves to the right, and then the 2's cancel out, we move this to the right, and it reduces the exponent, and so we see that this is this only has some exponent, presumably, that you could extract when a is equal to c, and that's only the case when b equals 0, and so that again would not be considered to be a triangle, right? So we can't extract exponents from the form cosine squared of theta and sine squared of theta, so we're stuck there. Okay, so now we make our final claim. So when a, b, c, and n are all integers, positive integers, this equation has solutions for n greater than or equal to 2 only if n is equal to 2. Okay, so we've already shown that it lives in this form. It has to be representable in this form. If we square both sides, then we end up with this form. Then cosine of theta and sine of theta have to be rational because we can't promote some exponent from the irrational values of it. So then this rational value has to equate to this rational value because this one can't promote anything. Right? So then the exponent is invariant from the left side to the right side. So rational value raised to an integer power, and a rational value raised to an integer power. From the left side, we see that the right-hand side has to have an integer power of 2, so n has to equal 2. Okay, so that was it. We spent way more time on this semester than I had intended. But all right, don't forget to submit your homeworks by tomorrow night.